I think we should go to the next presenter because time is running. So next, I'm calling Dr. Azlina Ramlee to present her topic on thermal and acoustic behavior of wall thermal insulation material made of treated fiber of oil palm empty fruit bunch and sugarcane bagasse fiber. Okay, you can start your presentation, Dr. Azlina Ramlee.
Okay. Hello, Assalamualaikum.
Salam, yes.
Okay.
Okay.
This restaurant. Yes. Okay. Can wait. This one. Did you see my screen?
Yes.
Oh, okay. All right. Wait. Okay. Assalamualaikum and very good evening. Today I'm Azlina Ramlee from Putra, Malaysia. I would like to present my project, which is thermal and acoustic behavior of wall thermal insulation materials made out of treatment fiber, oil palm and tree fruit bunch, and sugarcane bagasse fiber reinforced phenolic hybrid composite. Okay, a little bit about my presentation. First, I will introduce about the introduction, which is cover about OPEFB and SCB fiber. Later on, and move to methodology, and then characterization, which is cover for thermal gravimetric analysis, thermal conductivity, and the acoustics analysis. And then we next move to result discussion, and the last one is conclusion. Okay, basically, as we know, common this is agriculture residue, which is known as the oil palm, scientifically known as Elias genesis, is major industry sector that expand in a quick rate on global scale and has economic development due to the wide world demand. And the main chemical components of oil palm and tree fruit bunch fiber, of course, is content of cellulose, hemicellulose, lignin, and basically the major component of the biomass 40 to 50%, hemicellulose 20% to 30%, and the lignin 50% to 20%. Basically, I think everyone knows about this one. And sugarcane plant, scientifically known as a Saccharum officinarum, is an agricultural product that is cultivated all over the world, and the natural residue left after it. And we consider of this biomass and byproduct. So I tried to develop a new product, which is also the composite with the chemical treatment, which is I'm using the silane and the hydrogen peroxide, which is we can see from in the slide. This is the OPEFB fiber and drying and cleaning process, and also the sugarcane fiber, bagasse fiber cleaning and drying process. And then we next we move to fiber treatment, which I'm using 2% of silane and 4% of hydrogen peroxide. And then during this research, I'm using the phenolic resin as a metric, and mixed together with the OPFB and SCB, and then we use the hot press mold, and then we make it the composite. This is the composite formulation of treated OPFB and SCB fiber, which is ST stand for sealant treatment. I'm using the 5 different ratio, which is the first, the pure ST OPFB without mix anything. And then we move to another ratio, say 7 to 3, 5 to 5, 3 to 7, and then the last one, pure SCB. Basically, the biophenolic resin, we constant the content, which is quantity is 50% weight, and we may play around the mixing ratio, which is in between OPE fiber and SCB fiber. Same goes with the hydrogen treated composite. Okay, and then for the characterization, first we're using thermal. make it thermal. I'm using the TA instrument Q500, which is this equipment. And then the second one is thermal conductivity of treated fiber and SAB composite, hybrid composite analysis by using thermal properties analyzer quicklime TM30. And then this is characterization for acoustic, which is sound absorption coefficient, which is the sound absorption coefficient was measured with an impedance tube and the 2 microphone transfer function method. This test we carry out according to the ISO 10534 to 2000 standard. This is basically the schematic diagram. This is the real diagram in the lab. Okay, and then we have four different air gap thickness, which is 0 millimeter, 10 millimeter, 20 millimeter, and 30 millimeter air gap thickness. This is the schematic diagram, and then this is the sample, which is the small sample with the circle. We cutting in the circle shape and round shape 33 mm. Basically, this is the result TGA. We can see from here, from the table, we show that the ST silane treatment 5 OPEFB 5 to 5 SCB have the second highest of residue, the left residue. The first is SCB. So this is the variation of thermogrammetric analysis of silane treated of OPEFB and SC fiber phenolic resin, phenolic hybrid composite. So we can say that here, the sugarcane bagasse fiber is good in the thermal, in conducting in thermal stability. And then for hydrogen peroxide treated, we can see also the same ratio. 5 OPEFB and 2 5 SCB hydrogen treated. We can see the most highest left residue here, which is 58.69%, which is here. And for the first stage, thermal degradation of hybrid composite gives a small initial weight loss from 30 to 100 due to evaporation and loss of water molecules in fiber composite. And then the maximum rate of the weight loss was seen in the range of 250 to 500 for the composite silane treated samples, with the onset being above 200 degrees C. Silane treatment removed the hemicellulose and the lignin. The cellulose was exposed by the silane treatment and the silane coating on fiber, showing the improvement in thermal stability due to the better interfacial bonding. The thermal properties of treated hydrogen peroxide of OPEFB and SEB composite and hybrid composite revealed two-step of degradation process. Further weight loss was found in the first degradation stage with temperature range to 270 degrees C to 307 degrees C, indicating that thermal degradation of hemicellulose taught the thermal degradability of lignin and hemicellulose. Then hydrogen peroxide treatment increased the thermal stability performance also. Then for the thermal conductivity result, we found that the same ratio for 5 SCB, 5 OPFB to 5 SCB indicate the lowest thermal conductivity to make it the wall thermal insulation, which is 0.0542. So the result obtained that 2% of silane treated indicates the lowest value of thermal conductivity compared to other hybrid composite. So the equal ratio of treated oil palm and sugarcane bagasse seen as an ideal combination for the thermal insulating. The same trend was noticed for 4% hydrogen peroxide treated. The hybrid composite present the lowest value of thermal conductivity amongst hydrogen.
We have another 5 minutes, Dr. Azlina, you have another 5 minutes.
All right. The current work shows similar agreements. We reported for the thermal insulator, which is the best insulator is lower than 1 watt per meter Kelvin. So, and then we move to this is the acoustic analysis, which is have 4 different air gap. This is 0 mm, 10 mm, 2 mm, and the 20 mm and 30 mm, which is we can see from here from the graph, which is when we apply the air gap, the highest the air gap, the peak will be shifted on the right here, for here, and then we shifted to here. Why? This finding show that the result obtained are supported with previous investigation. We based on the physical after treatment surface, the oil pump and turbulation contain more void, and then we can see that the hydrophilic hollow structure tends to retain more compared to hydrophobic structure due to the greater quantity of open pores. Among the silane treated hybrid composite, see, we find also ST5 OPEFB 5 SCB hybrid composite show the highest sound absorption coefficient, and then air gap thickness also. After evaluating study with various air gap thickness, it was revealed that the silane treated hybrid composite with no air gap are better suited to conduct high frequency in the range of 2,500 to 4,500 Hz. Meanwhile, by applying air gap thickness, the frequency shifted to a lower frequency. Several parameters such as the fiber loading, types of fiber, fiber diameter, and pre-treatment of surface fiber influence to the increasing in sound absorption of the materials. So this is the next. Okay, the next is about the hydrogen. Hydrogen. Can move. Okay, hydrogen peroxide. Same goes with the same trend, but the same trend when we apply the air gap, the peak will shifted to the right. Okay, and then okay, we can see the treated HT OPEFB reinforced phenolic composite since has a good sound absorption behavior at high frequency, and then more than 2,000 Hz, and the sound absorption coefficient more than 0.5, which is mean from for acoustic analysis, the better is more the sound absorption must be more than 0.5, and then the 4% hydrogen peroxide treated sugarcane bagasse, we can indicate the lower sound absorption coefficient at high frequency range, but slightly higher peak at the low frequency range. For the removal of lignin, pectin, and hemicellulose of sugarcane bagasse fiber after hydrogen peroxide pretreatment give influence to the acoustic absorption performance. This kind of increasing, decreasing, and increasing pattern of peak are probably due to the specific characteristic behavior of natural fiber, reflecting sound at low frequency but absorbing sound in the middle and high range of frequency. The fluctuating curve in the sound absorption result was caused by the raw fiber wide range of diameter size also. All the peaks of the plots with air gaps are changed to lower frequency with higher thickness. 30 mm of air gap represent lower values of frequency. For the conclusion, it was concluded that 2% of silane pretreatment increased the performance of hybrid composite reinforced biophenolic resin compared to 4% hydrogen peroxide treatment. The result of silane treated 5 OPEFB to 5 SCB hybrid composite clearly indicates the improvement in thermal stability, low thermal conductivity, and the better sound absorption behavior than other hybrid composites. The utilization of cupping agents such as silane solution in fabrication process indicates the formation of strong link between the hydrophilic fiber and hydrophobic matrix in biocomposite, making it visible option for wall thermal insulation in energy efficient building application. Thank you so much.
Thank you very much to Dr. Nur Azlina Ramlee, Nordin, for her presentation. Now for the Q&A session, I would like to have 1 or 2 questions, please.
So I have a quick question. So first of all, I would like to thank Dr. Noor for the great presentation. I think it's very important. I mean, the acoustic and thermal insulation properties of different materials, and they are not often characterized in the literature. So I think it's a very good work. I have a quick question related to if you have done any comparison between like the fibers obtained, like the thermal and the acoustical properties of the fibers obtained from the empty fruit bunch compared to other sources of fibers from oil palm, like for instance from the trunk or from the like the fronds, like Dr. Afifa showed in the beginning. She was using fibers from the fronds. So have you done any comparison?
At the moment, I'm not complete yet the comparison. I mean, because for this project we have a lot of steps and then another parameter. So I don't have at the moment we don't have any we don't do any comparison. Maybe it's a good suggestion from you, and maybe we can I can do for the next process.
Mm-hmm. Yes, thank you so much for your answer.
As Midani just want to mention that she is going to give her viva. She just submitted the thesis, so she is waiting for the viva. So inshallah, the viva is maybe next month or something is going on. Mm-hmm. But what you call that, she is very dear. She just go through the maternity. Just she what you call that, delivered a baby just 1 week ago. So alhamdulillah, she is ready to come on that one. So congratulations, Azlina, for coming and giving the presentation. And she done a very good job, but unfortunately due to pandemic, she unable to work, and due to her health issues and all these things. Mm-hmm. So this is the good, we can look forward to work with the CAS and what you call to you, and we will work some comparative study with the 3-4 others dead palm fibers, means the palm-based varieties. This is a good suggestion. Thank you so much.
Thank you so much.
Yes, this would be highly appreciated. I mean, we would love to work on also characterizing thermal and acoustical insulation of other like date palm fibers panels. So perhaps we can collaborate in this as well. Thank you.
Inshallah, inshallah. Inshallah.
Okay. So we go to the next presentation. I
think we still have time. We can have take a question from Dr. Qais. We still have 6 minutes for the next presentation, so perhaps we can have questions from Dr. Qais.
Okay, thank you very much, and congratulations, Dr. Noor, and it's a good presentation. I have just a quick question about the control of the density. You vary in the density of your produced material because it generates the porosity with a K of the insulating, acoustic insulating. Thank you.
For this project, I also do a characterization on for the density, void content, the tensile in mechanical, physical. So all the aspects we investigate actually for like the physical, mechanical density. Everything is we do in separate chapter actually. So for the density in another chapter. So I also investigate about this one. So because it related to the next step for the wall thermal insulation. So
inshallah.
Yeah. It's already complete actually for the density topic, but it's not in this conference.
So maybe one last question from me, Dr. Noor Azlina. Maybe last question from me. How many the area of the sugarcane base in our country, sugarcane plantation? How big the area?
We cover on actually the biggest one in the Perlis and in Perlis and Kedah, which is I think around I can't remember, but in my research I also jot down that one in the introduction part. I think it's about 24 million hectare the areas cover, yeah. Basically we are in the Perlis, Kedah, Malaysia for Malaysia cover. But in Asian also we have another statistic about the area cover about that one.
Okay.
Okay. Thank you, Doctor.
Okay, thank you.